Okay, let's see the contents of this video. First, I will explain about the two-dimensional discrete Fourier transform, its applications and limitations. Then I will explain the Matlab code for two-dimensional DFT of a square function, and I will take one example of the natural image. I will also explain you about the various types of filters such as low pass and high pass ideal filter, Butterworth filters and the Gaussian filters. Then I will explain the Matlab codes to implement the frequency response of these filters. Then I will show you that how you can do the frequency domain filtering of noisy images. And then I will explain the Matlab code for image filtering using these implemented filters. And after that, I will explain the Matlab code for removing a particular frequency using a notch filter. So let us start this session. But before going ahead, I recommend you to watch following my two videos. The first one is about the discrete cosine transform of image and image compression. This link is given in the description. This video is about the DCT. As you know, that DCT is an extension of the DFT. The DFT has actually the complex values in its spectrum, while the DCT has the real values in its spectrum. And as you know, the DCT is very popular in the image and video compression. So you can have the good idea about the DCT and its implementation using Matlab. And the second video is about the wavelet transform analysis of images using Matlab and Simulink. Its link is also given in the description, and if you go through this video, you will be able to see that how an image can be decomposed into the different frequency labels using wavelet transform. So these two videos are very useful. If you want to go through them, you will learn a lot of new things. So now let us come to this current topic, that is discrete Fourier transform. But before going to the DFT, I am giving the background of the DTFT. So that is the discrete Fourier transform. Actually, the discrete time Fourier transform represents an image as a sum of the complex exponentials of varying magnitudes, frequencies and phases. Actually, it's a natural form of your Fourier transform. So it comes first. DFT is just extension of the DTFT or modification over the DTFT. I will show you how. For an image fxy, let's say its size is m by n, then DTFT can be computed by the following equation. So you get f omega 1 omega 2 as the output. It is known as the spectrum of the image, and this you can achieve by this equation. And here this f omega 1 omega 2 is complex valued, and it's a continuous function of omega, and it is also a periodic function of omega with a period 2 pi. And because of this periodicity, usually it is displayed from the minus pi to plus pi, I mean for the 2 pi. And the component f00, f00 means you can get f00 for omega 1 equal to 0 and omega 2 equal to 0. So when you put omega 1 equal to 0, omega 2 equal to 0, you get this f00. Of course, it's a sum of all the values of image fxy. For this reason, f00 is known as the DC component. Why DC component? Because for omega 1 equal to 0, omega 2 equal to 0, there is no frequency. So since there is no frequency, that's why it is known as the direct current or the DC component of the image. And this f omega 1 omega 2, as I said, it's a complex value. That's why it can be broken into the two pieces. One is the mod of it, that is the magnitude of this spectrum. So it is known as the magnitude spectrum. And second one is the angle f omega 1 omega 2. Of course, that will be known as the phase spectrum. And the inverse exits, that means you can get your image back from its spectrum f omega 1 omega 2 by the following equation. So fxy equal to 1 upon 4 pi square integral. Here you can see that we have used integral instead of summation, because as I said, the f omega 1 omega 2 is the continuous function of omega. That's why we have used integration. And this equation, if you interpret this equation, you can see that fxy can be represented into the sum of infinite number of these complex exponentials, I mean these sinusoidal waves of different frequencies. And the f omega 1 omega 2, as I said, it's a continuous function of omega. Therefore, this computation is not suitable for the computers because the computer is a discrete device. Computer cannot evaluate a continuous function of a variable. It always can give the discrete samples or discrete values of a continuous function. So what to do? So to make it feasible for a computation on the computer, the f omega 1 and omega 2, which is a continuous function of omega, it has to be discretized. Therefore, this continuous function is sampled to get the discrete values. Yes, this is the basics of the DFT. So the discrete Fourier transform represents the sampled versions, the discrete version of this continuous spectrum of DTFT. So that is the relationship between the DTFT and the DFT. So what you will say now, the DTFT is a normal frequency transform of your signal. It gives a continuous function of omega, which is not suitable for the computers for the computation. So what we are doing, instead of getting a continuous function of omega, in the DFT, we are getting a discrete version of this spectrum. Okay, so for an image fxy, which has the size, let's say m by n, the DFT can be computed by this equation. So FUV is a spectrum. It is similar to f omega 1 omega 2. Here we are using the different variable representation u and v instead of omega 1 and omega 2. And this equation is easy to implement in the software. You can write 4 for loops, actually the 2 for loops for x and y, and then 2 for loops for u and v. So how this equation is computed? Actually, first we keep the values of u and v. Let's say u equal to 0, v equal to 0 you put in this equation, and then we varies the value of x and y. Similarly, we change the values of u and v. For example, u equal to 0, then v equal to 1, and then again we run these two summations from 0 to m minus 1, y equal to 0 to n minus 1. So for covering all the pixel locations u and v, we repeat these equations. So it is easy to write in software. And the DFT coefficients, as I said, these are the samples of DTFT. So they have this relation. So you can see that your discrete Fourier transform is equivalent to your DTFT for the following frequency values. Omega 1 is the 2 pi u by m, and omega 2 is 2 pi v by n, where u is varying from 0 to m minus 1 and v is varying from 0 to n minus 1. So now inverse DFT exists, and you can get your image back from the samples of the DFT by the following equation. So if you apply this equation, you can get your image back. So from the spectrum, you get your image. Again, this equation you can implement using 4 for loops. So first you substitute the values of x and y, then you run these 2 for loops for u equal to 0 and v equal to 0. Now let us see the DFT applications and limitations. So DFT has many applications. Of course, the first one is a spectral analysis of the signals. So if you have the spectrum of a particular signal or image, you can simply visualize for getting information that how the different frequency spectral components have their variations, their magnitude in different dimensions. So we have the ideas about the frequency contents of the image or signal, and on the basis of that information we can design the different types of filters. What range of the frequency you want to allow and what range of the frequency you want to attenuate. And you can also find a system's response using the DFT also in the fast way, because the DFT equations which I have explained, they are computationally heavy. They require lots of multiplications and additions. To get a fast DFT computation, we have the fast algorithms with us. They are known as the FFT, the fast Fourier transform. So these algorithms have the capability to compute the DFT in the fewer computations. Okay, so if we use the FFT, we can compute DFT in very less computations, which is suitable for the computers. And as I said, we can find the system response because we know that for a system the output y you can achieve by the convolution of input and the system impulse response. So this is yt, and this is your system whose impulse response is st, and this is your input xt. So this yt is actually achieved by convolution of input and your system's impulse response. So this convolution requires lots of computations. This you can implement this equation in frequency domain also. So if you take Fourier transform of it, you get yj omega equal to xj omega multiplied with hj omega. You know by the convolution theorem that convolution in time domain becomes multiplication in frequency domain. So multiplication is much easier than computing convolution. So to implement this equation is easy. So with help of the FFT, we just convert ht into h omega, we convert xt into x omega, we multiply it, and then we take inverse transform to get our signal or response yt. So this is how we can achieve the system response with help of DFT. And of course, we can apply various filters on images to get the enhancements and restorations. And also we can achieve the correlation also between the two images. This technique is actually used to find a particular pattern in an image. So DFT has a few limitations also. As I said, the DFT spectrum is complex, and it has both magnitude and phase spectrum, and it has no sparse representation. It means every coefficient is important in magnitude and phase spectrum. So unlike the DCT or wavelet, it doesn't give the sparse representation, or it doesn't show the energy compaction. And also the DFT spectrum presents only the magnitude versus frequency information. So either you get FUV or F omega 1 omega 2. You have the information of magnitude versus frequency, I mean omega versus the magnitude. So no time information is visible in this spectrum. So you cannot have the idea that what changes occur to the signal or image or at what particular time or location. So this information is missing in the DFT. If you go to the wavelet transform, you have the capability where you can visualize both frequency and the time information simultaneously. And now let us see how we can compute the DFT of a two-dimensional square function. So for this, I have taken one image. You can see this image which has one square function at the center, and this same image you can visualize in 3D. Actually this base is being represented by the value zeros, and this top is represented by the value 1. So this is your simple square function in the spatial domain. And if you take the DFT of this image, you get this type of spectrum. So this is your FUV, FUB. So you can say that this is your U direction and this is your V direction. So this is your FUB. Here the picture is not giving much information. If you see this picture in 3-dimensional, then you can have the better idea. So this is the spectrum of this square function. Okay, so this is the spectrum, I mean the FUV. So we have taken the DFT of this square function and you are getting the FUV like this. So here you can see the clear variations that at the center where U equal to 0 and V equal to 0, so you are getting the F00. So this peak is representing the F00. So that means it is the DC component of the image. So that is the largest one available in the frequency spectrum. And this is one more example where I have taken one natural image of this Lena, and this is its corresponding frequency. So in this spectrum FUV, you can see the center part, which is the brightest in the image. So brightest in the image means it has the highest magnitude. So that you can visualize here. So I have just shown you a cut section at the center. So you can see that this is actually your F00 value of the spectrum, which is lying at the U equal to 0, V equal to 0. So which is your representing the DC content available in the image, and these are few AC components available in the image. So you can see all those AC coefficients, the small variations in the amplitude. So these coefficients are actually representing the high frequency, and this one of course is representing the DC coefficients, and near this these are actually the low frequency components. So this is what about the spectrum of images. Now let's go to this Matlab code that will compute the two-dimensional DFT of this square function, which I have already shown you, and then natural image, which I have just shown you. So for this we are reading few images. So these f0, f1, f2, these are actually the three images, and all are of the square function, but they are of the different size. So f0 is representing a small square, while f1 is slightly bigger than f0, and f2 is bigger than f1, and this fourth image img is actually image of that Lena. And by these commands we are getting the magnitude spectrum. So here you can see that we have used the Matlab's FFT2 function for computing the Fourier spectrum, I mean the DFT of the first image f0. Then we are shifting this spectrum to the center. Actually if we compute the FFT2 only, we get only the quarter part of the spectrum. So as per the convention, let's say this is the v axis and this is the u axis, we get only one quarter of the complete spectrum as for the visualization. So if we can shift this into the center, we can get a complete spectrum like this. I mean this full spectrum has to be shifted to the center. So this point is now transferred to this point. Okay, so let's say if this is image is of size m by n, if this is your size m and this is the size n, then the center will be, of course, will be at m by 2 and n by 2. Your center will be m by 2 and n by 2. So this is done by FFT shift, so that you can have the full spectrum of size m by n for the visualization. And then we are using the absolute because we are finding the magnitude, since spectrum has the complex values, so you cannot plot it. So we are finding its magnitude by absolute function. And these are the commands just for plotting these images and their corresponding spectrum. And here you can see that we are plotting the spectrum of each image, I mean image 1, image 2 and image 3. And for plotting I'm using the imshow function, but directly putting f0, that means the spectrum, I'm using actually the log 1 plus f0. Why I'm using it? Because if you directly use f0 for imshow, then you will get image, but you will get a darker image, because as you have seen that the f00 component is of very large magnitude as compared to the other frequency components. So there is a huge difference between the magnitudes of these spectral components. So therefore, if you use directly imshow f0, your image will look more darker and you will not be able to see the shapes correctly. So if you take log, the difference between the magnitudes will be small, and now you will be able to visualize the details available in the image. And one is used just to ensure that if f0 has somewhere 0, so the log will 1 will take care of the log. And to visualize the spectrum in 3D, I have used just mesh command. So let us run this program into the Matlab, and let me see what type of output I will achieve. So I am jumping to my Matlab editor, and this program I have already written to save the time, so I am just running this program. Okay, I achieved the output, and here you can see that this is my first output, where you can see that this is a square function. Your first image f0, this is the second image f1, and this is the third image f2. As I said, all are square functions but of different sizes, and these are magnitude spectrum of this image, and this is actually it's a 3D view of the spectrum. So you can visualize the difference. You can see from here that if you go to the higher sizes of these square function in spatial domain, you can see that the corresponding effect in the frequency domain is that the spectrum is becoming more sharper and sharper. Actually, this is showing the property of the Fourier transform. It says that good time resolution is equivalent to the poor frequency resolution, and the poor time resolution is equivalent to the good frequency resolutions. That means the sharper you are, more sharper you are in the spatial domain, the more coarser you will be in the frequency domain. So that is one special property of the Fourier transform. And it is evident from the theory that for a delta t, you get a constant function in the frequency domain, and for a constant function in the time domain, you get the delta omega in the frequency domain. So these are two limits of this property. And for natural image, you can see that this is your linear image, and this is the corresponding spectrum. So at the center, you can see the brightest point, which is actually showing the DC content of the image. I can show this into the 3D also. So its spectrum was FIMG, and just pressing the mesh, it will plot its 3D. So this is actually the 3D view of this spectrum, and you can easily see that at center you are getting the f00, which is of the highest magnitude. So this is how you can plot the spectrum of any image in the Matlab. And now let's see various types of low pass filters. We have three main low pass filters: ideal, Gaussian, and the Butterworth. And these are their mathematical expressions. I mean their frequency response, how their frequency response is computed as HUV is computed like this. Here DUV is actually the distance of your current pixel location, and D naught is a given value. So that will decide the size of the filter. So I will explain by showing its shape. So here you can have the better idea. So this is your filter from the top view, and this is its 3D view. So what is D0 actually? So D0 actually here is its radius from the center. So this you can visualize more in this diagram. And here you can see that all distances which are lesser than D0, the value is 1. That's why you are getting a white pixel. So all pixel values are 1 here. And for all distances which are greater than D0, you are getting the 0. That means this black area is being represented by the 0 values. So this is how you can compute the filter response. And similarly, we have this equation for Gaussian filter. So for a defined D0, for all different values of the distance from the center, I mean this DUV, you get this type of shape. So from the top, this is the view, and this is the 3D view. And here you can see that how we can change the shape of this filter by having the different values of D0. So if your D0 is increasing, your filter is becoming more flat. And for the Butterworth filter, it is an equation for nth order Butterworth filter. And here again, you can see from this shape that if for increasing order, I mean from n equal to 1, 2, 3, 4, you can see that this transition is becoming more sharper for higher order filter. And if you increase further, if you increase the order further, you can actually reaching towards the ideal. So these are a few popular low pass filters which are widely used. So we will use them in our video also. And now let us see the high pass filters. So again, the same category, the ideal one, Gaussian, and the Butterworth high pass filter. So these are their mathematical representation, and these are their pictorial view. So here you can see that the ideal high pass filter is just inverse of the ideal low pass filter. So there you got this circle of the white color and this background of black color, and now here you are getting just inverse. So the same is clearly visible from this line diagram. So for a particular certain frequency from the 0, I mean for the distance d0, all the frequency will be eliminated by the frequencies which are higher. I mean after this frequency, they all will be allowed. So same is true for this Gaussian filter and the Butterworth filter. The difference is only that here the cutoff of the frequency is abrupt, while in these two cases the cutoff of the frequency is gradual. That means frequencies are attenuated gradually. And now let us see the program to implement these filters frequency response. So here we will implement the HUV. That means we will implement all those equations which are based on the DUV distance equation. We will implement those equations here to compute this HUV. So here we have taken the size M or N. That means we will generate a filter response HUV of size 200 by 200. And the distance is given 20, and n equal to 1, that will be used for Butterworth filter. That means we will implement the first order. So you can implement actually the any order if you change n equal to this value. So here by the first line, if you execute this, you are executing this function myFilter2D, and we are passing these attributes. So that means the first attribute is the type of the filter. So that is the ideal LPF. Here we are defining the size, and here we are giving that distance 20. So after executing this line, you will be able to get the HUV of low pass filter, which is ideal, and it has the radius 20. Similarly, with this line, when this function is executed, your Butterworth LPF will be created with a defined size M by N, defined distance, and then order of the filter. And for this Gaussian filter, again for the same function, you're defining the type of function and then size of function and then distance given for that HUV. And here by these three lines you will get the filter response for high pass filter. So these three are low pass filter and these three are high pass filters. And these are actually the plot commands to plot the frequency response HUV of these all 6 filters. Now let us see what is this function myFilter2D. Actually this myFilter2D is not a Matlab filter. This is my own filter which I have coded to give you this frequency response. So later in the coming slides I will explain what is inside this myFilter2D. And here these are just plot commands to plot all the filter responses, and I have used the top view and then 3D view also. So we have 3 filters, 3 LPF filters and 3 high pass filters, and I'm using the top view as well as 3D view of all the HUV. So that's why I'm getting total 6 and 6, 12 images in the output. So let me execute this program in the Matlab, and let us see what type of filter response I will achieve. Okay, now let me see what is, as I said, what is inside this function myFilter2D. So in the myFilter2D, I have actually given these attributes. I mean the filter type, its size, and the radius, and the order, which will be used only for Butterworth. So this is the syntax. And first thing what I am doing here, I am getting the center of the filter response or image. Okay, so for the filter of size M by M or M by N, let's say this is your output HUV. First I am getting its center. So this is the center PQ. So where P is obviously the M by 2 and Q is obviously the N by 2. So this is I'm getting the center, and here I am initializing the distance matrix as well as this H matrix. So here I have used a switch case. So for the case 1, when the input type is the ideal low pass filter, I have implemented this code. So this code is nothing, it is just the same mathematical expression which I have already shown you. Just go to the previous slides. So I have already shown you this equation. So I have implemented this equation for ideal low pass filter. Similarly, I will implement this equation for Gaussian and this equation for Butterworth filter. So in that code, I have just used these mathematical expressions. So here you can see that the first distance is calculated. So this distance is actually d equal to square root your current pixel location u and then your center location plus v minus q square. So this is how this distance is calculated from the center, and this distance is given into this if condition. So if the computed distance is lesser than d0, you assign the HUV equal to 1. Okay, so this is how you get your filter response for ideal low pass filter. Similarly, I have used that equation for Butterworth filter. So that was your 1 upon 1 plus d upon d naught power 2n. So, and similarly for that Gaussian, that was your e power minus d square upon 2d square. And these codes are for ideal HPF, and this is for Butterworth HPF, and this is for Gaussian HPF. Okay, so I have done nothing special here. I have just implemented those equations which I have already shown you. So now let me run this program to generate the filter responses for all these 6 types of filters. So I am jumping to my Matlab editor, and this is the code which I have already written. And this my filter 2D is this function which I have just explained you. It is also written there. So let me run this program, my filters 2D, just running it. And yes, I got this images. So here you can see that this is the low pass filter HUV top view, and it is the 3D view. And this is your Butterworth low pass filter, it's 3D view, and this is Gaussian low pass filter and it's 3-dimensional view. So you can visualize that what type of filters are these. And similarly, I have achieved 6 more plots for high pass filters. So these are your top views and these are your 3-dimensional views. So this is your high pass, ideal high pass filter, and it is corresponding 3-dimensional view. And this is your Butterworth and this is a Gaussian. Okay, so this is how you can get the filter response HUV with help of this program. So this program or this function my filter 2D will directly be used in the frequency domain filtering. So let's see how. So now let us come to the frequency domain filtering of noisy images. So this is the scheme. So what actually we do, we have let's say an input image which is actually the noisy. So this is your noisy input image fxy. First we take DFT of it, so it is converted into FUV. We have the filter response HUV, so we choose HUV depending on our applications. If we are applying low pass filter, we will choose HUV of low pass, and we have further choices, either we will choose ideal, Butterworth or Gaussian, etc. And in frequency domain, what we will do, we will simply multiply this frequency response of filter and then DFT of the image. So we multiplied F and H like this. So when you multiply these two spectrums, we get another spectrum, which is the spectrum of the filtered image. So GUV is actually representing your filtered image in frequency domain. So we take IDFT and we get this GXY, that is the filtered image. Okay, so this is the simple and basic scheme of image filtering in the frequency domain. So for this, I have written the Matlab code so that you can see with these lines of code, when you execute it with the UI get file, a system dialog box appears that will ask you to choose your image that has to be filtered. So with this IMRead, that image will go to IMG variable, and here we are getting its size, I mean the rows and columns, And then with this line, we are finding the FFT, or I mean the DFT of this image. Okay, so the capital F is carrying the DFT information of this input image, and then we are shifting this spectrum so that we get the full spectrum at the center. Then we are implementing the HUV, I mean the filter response, with help of this filter, my filter 2D, which I have already explained in the previous slides. And here you can see that I'm implementing, let's say, Gaussian LPF with the defined rows and columns. This is important things to be noted, because the filter size and the image size must be of the same size, because we have to multiply the spectrum of both. So if their size is not equal, obviously you will get error during the multiplication. So that's why the same rows and columns I'm using here. And the 50 is actually the distance D0 to implement this filter, Gaussian low pass filter. So once this HUV is computed, we are simply multiplying, this is the spectrum Fs of your image, and this is the spectrum of your filter. So this is the spectrum of your filtered image. Actually, according to the previous slide, this is equivalent to actually the GUV equal to FUV multiplied with HUV. So this equation is equivalent to this. And now taking the inverse Fourier transform, I'm getting my image, but it is in a double format. So just and it is also complex. So I'm just taking the real part of this and converting this into the unsigned integer 8 type to get my image in IMGR, so I can visualize it. And these are few plot commands that will plot your input image and the magnitude spectrum, and it will plot your filtered image and then the magnitude spectrum of the filtered image. So you can compare that what type of input output I have. So let me jump to the Matlab and run this program. So this is my editor, and this is my program which is already written. So here you can see that I have used the ideal low pass filter right now, and its radius is 50. So let me run this and let us see what type of output I will achieve. So I'm running it and it is asking me to choose my file. So I'm choosing this file or image, Lena, and let's see what output I achieve. Yes. So this is the output which I am getting. So this is my original input image, and this is corresponding spectrum, and this is the filter image, and this is the spectrum of this filtered image. So you can see that that your ideal low pass filter is applied. So here you can see that all the high frequencies are eliminated, just the central low frequencies along with these DC components are preserved. So that's why you are getting this image. So what type of image you will achieve? Obviously you will get a blur image, because the all high frequencies information is eliminated. I mean high frequencies are there generally in the sharpness or edges. So obviously since I have now the low frequencies, so I will get a blurred version of image. So I'm getting obviously a blur image. You can compare the both, and let me just show you the this image in zoom format. So here you can see that this is your output, this is your original image, and this is your filtered image. But look carefully, although this image is blurry, but there is some problem. If you have noticed, if you can notice that these are lots of repetitions of the edges, okay, everywhere near the edges you can see there is a lots of repetitions of these edges. So something like you can say that this is oscillations in the intensities. This actually is known as ringing artifacts. What is this actually, the ringing artifacts? Let me explain you. This happens because of this ideal low pass filter. So in this ideal low pass filter, you are simply neglecting the high frequency components abruptly. As you know, if you go to your spectrum, you see that your ideal low pass filter is like this. So that means you are simply neglecting these high frequencies abruptly, and because of this you get this ringing artifacts. So this is accordance to the Gibbs phenomena. If you have the idea of the Gibbs phenomena, so Gibbs phenomenon says that at the edges, there is a heavy oscillations of function. Okay, so the same is visible here. If you are watching from the top, so there is a lots of oscillations near the edges we are getting in this image. So how to actually get rid of this type of ringing artifacts? The answer is actually, instead of cutting these coefficients abruptly, we have to cut them gradually. So that's why the Gaussian filter and the Butterworth filter came in importance. If you see their frequency response, instead of this abrupt cutting, they have the smooth transition, and because of that we get very small oscillations, or I mean the neglected oscillations. So let me run the program for the Gaussian filter instead of this ideal filter. So I'm changing my filter, let's say Gaussian filter, with the same radius. Let me reduce it, let's say 30, and let's see whether I will get the ringing effect or not. So I'm running it and I'm choosing Lena again, and let's see. Okay, and here you can see that you get this filtered image, which is of course a blur version of this input image. But if you see closely and if you compare this with the ideal low pass filter, here the ringing artifact is not visible. So that's why we choose, or we prefer, the Gaussian filter over the ideal filters to avoid such types of unnecessary ringing or artifacts. Okay, the similar output you can achieve from the Butterworth filter also, because it also has the smooth transition. And now let me show you one example of the high pass filtering. So instead of LPF, I will take the HPF. So I'm taking the Gaussian HPF, and let me run this program. And instead of this Lena, let me choose another image, let's say this text image. And yes, here you can see that this high pass filter is applied. So this is the input image, and this is its spectrum, and this is the output image. So let me show you the enlarged version. And in this enlarged version, you can see that all edges are more dominant than the smooth area, because since it is a high pass filter, only the high frequencies are allowed to pass, no low frequencies allowed to pass. That's why you are getting this type of output. And since I have applied the Gaussian high pass filter, so there is no ringing effect you can see in this image. And I can take the Lena image also for the same high pass filter. Let me see what type of output I will get, and this is the output. So here again you can see that edges are more highlighted because of this high pass filter. Now let me jump back to my presentation, and now I will show you one example where you can remove a single frequency from a noisy image with help of a noise filter. So actually just consider the same Lena image. This is your image, and it is the corresponding spectrum. And now I corrupt this image with help of some sinusoidal noise like this. So a sinusoidal noise is added to this image, and now let us see what happened to its spectrum because of this. So just see the difference of this spectrum. Yes, if you compare this spectrum with the previous one, you can see that now we have these two bright spots in this spectrum of this noisy image, which were not visible in the original image. So actually these two parts are showing the contribution of this sinusoidal noise. So now how we can remove this noise? Obviously, if we can remove these two white spots, we can remove this sinusoidal noise from this image. So what type of filter we need? Obviously we need this type of filter. So here you can see that this filter is white in the color all over. That means all pixel values are 1 except these notches which has the values 0, because when these two spectrums will be multiplied, so this is your actually the FUV, and I mean the spectrum of your image, and this is the spectrum of your filter HUV. So when these two will be multiplied, obviously because of this white area, I mean the values 1, all frequencies will be preserved, I mean they all will be passed as it is, except these white spots, because they will be multiplied with the value 0. So they will be eliminated. And since they are contributed by that sinusoidal noise, since they are eliminated, of course, then noise should also be eliminated. So let us see how we can achieve it. This type of filter, obviously, we can design it manually in some some software such as MS Paint, or you can create this in Matlab also. And just save this image as grayscale image in your current directory. So I created this in MS Paint and save this image as a grayscale image. Okay, so now you can visualize this in 3-dimensional also. So this is your HUV, and here you can see that all frequencies will be multiplied with a 1 except these frequencies which are multiplied by the 0. So they will be eliminated. So now let me come to the program. This is a simple code which can be used to create that sinusoidal noise in the Lena image. So it's a simple just for a time vector from 0 to 511. Because the size of the Lena is 512 by 512, that's why this vector is from 0 to 511. And we have created a sine wave, sine t plus 1. Plus 1 is we have shifted up this sine wave, and then with the repeat matrix we have repeated this one-dimensional. Since this is 1D, so we have to create a 2D. So now n is a 2D matrix of size 512 by 512. So n is just a pure sine wave in 2 dimensions. So to create the noisy image, we have added the image f and then this noisy image, sine image, multiplied with the 20. Actually, this is, you can say, it's a embedding strength. So if you increase this number, the impression will be more. If you decrease this number, the noise impressions will be less in the image. And now how to actually implement this scheme? We will use the same program which I have just shown you. So instead of this line in the previous program, I will use these two lines. So I will simply remove this line from the previous program, and I will use this line. So here I am reading the filters response h equal to I am read. This is the name of the image which I have shown you in the previous slide, which was saved in the local directory or in the current directory. And then this h is divided by 255 because it was saved as a grayscale image. So the values were 0s and 255 all over the image. But I need only the values 0 and 1 for the multiplication purpose. So I have divided all the values by 255. So now h has the values only 0s and 1. So it is 1 all over except those two notches which has 0 values. So now let me go to the editor and run this program. And as I said that in this program, I will simply disable this line. So I will make it comment, and then I will uncomment these two lines. So that means I am reading that mask lena 1.bmp. So let me show you what type of image is this. So in this current directory, this is mask lena 1.jpg or bmp. So this filter response I have already shown you in my previous slides. Okay, so I will read this image and I will consider this as the HUV of the filter that will be applied on the image. So let me run this program. So it is asking me to choose image. So this is a noisy image which I have already created and saved in the current directory with help of I am right. You can also do in your case. So I have taken this noisy image and just selecting it, and yes, I got the output. Now see this output. So this is your noisy image. You can see a sinusoidal impression on this image, and this is the corresponding spectrum. So here you can see that these two bright spots are visible, which were not available in a original image. So I have to remove these bright spots. So for that I have used the filter, and here you can see that with these black color, I mean these extra frequency components, which are the contribution of this sinusoidal noise, are now eliminated. And after taking the inverse Fourier transform, you get this output. So in the filtered output, you can see that that noise is almost completely removed. I can show this with the zoom version. So this is your input and this is your output. So you can see I have almost completely removed, almost few impressions are there near the borders, but the output is quite impressive in this case. So this is how you can eliminate a particular frequency. Even you can eliminate a set of frequencies also. Suppose the same image is corrupted by the more than one frequency. So you have to just identify these spots, I mean the extra spectral coefficients which are contributed by the noise, and according to them you can design your filter response HUV, and then you can multiply it to remove those extra frequency or spectral components. So this is how you can go for frequency domain filtering with help of these filters. I hope that you have enjoyed this video, and I really thank you all for this lengthy video, because lots of things I have to cover in this video, because I do not want to leave anything. So please like this video and share it to the maximum. Goodbye.